Hello, everyone. Welcome to the class. I wanted to make sure that you guys can hear me. So please try type something in the group chat. Okay, sounds good. Yeah. So most of you can. Yeah, if you can't hear me, just write something and then let me know so we can adjust the technology. So I'm gonna do something that's slightly different today. I'm gonna to allow me to switch back and forth more easily between slides and writing and board. I'm gonna try sharing only my iPad screen, and I'm gonna present both the PowerPoint slides and the writing part of the lectures from the iPad itself. So luckily, Apple Pencil just arrived yesterday. I get to play with it for a little bit to get the familiarity. So it will be a lot better, and we'll be able to do more examples that are writing in terms of writing on the board. Another thing that I'd like to emphasize before starting the lecture is that one of the things that I didn't quite like about last time's lecture is a lack of interactivity. So I would encourage you to keep typing into the group chat messages with your questions, and I'll just respond like a YouTube streamer using voiceover, and then I'm gonna repeat the question and respond directly your typed up group chat. On the other hand, my TA is also going to be monitoring the group chat. So in case there are any burning questions that he thinks that it's important to address right away, and then he'll let me know. All right, so that's the plan today. So we're going to be finishing up the convex function today, and then talk about the convex optimization basics. And after today's lecture, you should be able to tell whether an optimization problem is convex or not convex, to convert one optimization problem to another while preserving the convex optimization, and reformulating, say, optimization problems that are not necessarily convex using a set of rules so that you can convert them into convex functions. So that's a plan for today's lecture. So let me start sharing the screen. Okay, so I think you guys should be able to see it. All right, so it will be like this, and I guess I'm gonna also try writing something. Okay, so looks like it's working. All right, so all right, so let's first of all, the last part of the last lecture was on convex sets. So again, the definition of the convex set, think about it as a geometric body that if you connect any 2 points as inside this set, and okay, so someone pointed out there's an audio glitch, but is it better now? Has it recovered? Okay, great. The definition of a convex set, you should just remember it like this. If you take any 2 points within the set, and if you take the get the line segment among between these 2 sets, and if the entire line segment is inside the set again, then this set is convex, right? So this is a test of convex set. So that allows us to also do an arbitrary convex combination of points by induction. So a convex Hall of, say, the non-convex set on the right-hand side with this kidney shape would be, well, connecting this like that. So the set that looks like that would be the convex Hall of all the points inside this non-convex set. So with this CONV objects, then we are able to convert any set of points and any set into a convex set. Okay. So today, the first topic today is going to be about convex functions. So we talked about the definition last time. So again, the definition of convex function is that if you take the convex combination of any 2 points in the domain of this function, and the evaluation of the function at the anywhere in the middle between these 2 points needs to be lower, needs to be smaller than the linear interpolation of the function itself, right? So this is a linear interpolation of function itself on the right-hand side. On the left-hand side of the inequality, so that's the evaluation of the function somewhere in between these 2 points. So if this condition is satisfied for any interpolation for any 2 points x and y in the domain, then we say this function is convex. So again, there's convex function, there's also concave function. So these definitions are somewhat misleading if this is the first time that you're seeing this. So it's a good idea to remember convex function to be a cup shape, and the concave function is just the negation of the convex function by adding a minus sign. So if any function is concave, then minus of that function is going to be convex, right? So this will come back. So I'd like to also add like 2 important modifiers of convex functions. So sometimes we're interested in stronger definitions than just convex functions. In particular, we can talk about strictly convex functions, which simply makes the definition the strict inequality for any pairs of points x and y. So this ensures that this function f has like at least a little bit of curvature everywhere. Strongly convex functions, on the other hand, is something that's even stronger than strict convexity, which we require that if we subtract a quadratic function from the function f itself, then it remains convex, right? So any strongly convex functions is also strictly convex and also convex, right? So just to give a few examples of a convex function strongly convex function than strictly convex functions. So think about the univariate function absolute value. So this function is clearly convex. So if you look at the shape of it, then it looks like this. So this function is convex, but not strictly convex, because if you take 2 points here, x and y, and the linear interpolation at the middle we'll have this equal sign rather than strictly smaller than, right? So what is a strictly convex function? Okay, so fx equal to say x squared, so that will give you a quadratic function in a bell shape. If you take any 2 points and take the linear interpolation, the thing in the middle is always strictly bigger than the function evaluation itself over here, right? If you take any 2 points and the one in the middle, so this is always strictly smaller than that coming from the linear interpolation of the function. So how about like some functions as so again, this is of course strongly convex. It's actually one strongly convex with parameter m equal to 1. So what is a function that's strictly convex but not strongly convex, right? So well, you can I guess you can maybe think about functions that looks like this, right? So fx equals to 1 over x supported on x greater than 0, right? So this function is clearly strictly convex because you have curvature everywhere, but it is not really strongly convex because you cannot subtract any quadratic function from it while retaining its convexity. All right. So so some more examples of convex functions. So exponential functions is always a convex function. Power functions are also convex functions when the power a is larger than 1, or when the power a is smaller than 0. So I encourage you to try out the power functions with a between 0 and 1. Okay. By the way, like if there are any questions, I'll periodically look at a Zoom group chat. So if you have any questions, just write it and I'll respond to it and after repeating your question. Power functions, I guess power functions between 0 and 1. So think about the square root function when alpha is half, then this is clearly not a convex function, right? But if x is non-negative, then you can clearly tell that those functions are actually concave functions, because minus of x to the power of a when a is between 0 and 1 is a convex function. Logarithmic functions is concave, right? So think about the growth of logarithmic function. It grows like this. So you have, as x gets larger, you have diminishing return. So that gives you something that's curving down rather than curving up. All right. So Fn functions, well, so this is just a linear function with an additional offset b. So Fn function is the only kind of functions that are simultaneously convex and concave. So this is arguably saying that if you curve it, so this is a flat line or a hyperplane. If the surface is curved a little bit up, then it becomes convex. If the surface curved a little bit down, then it becomes concave. So this is a marginally convex case where the convex interpolation of any 2 points gives you exact equal in that function itself. Quadratic functions are convex under one important condition, right? So the quadratic functions are convex provided that the quadratic term is this matrix that defines the quadratic function is positive semi-definite. So again, the definition of positive the definition of positive semi-definite is that Q, we're using notations like this, is equivalent to, for any x transpose q, x is larger than 0, right? So you can we'll see how to prove it in the next couple of slides. Least square functions is a particular quadratic function because because if you expand it, you end up getting x transpose. You get x transpose a x plus like y transpose y minus the cross terms, which gives you 2 times y transpose a x, right? So this function is a particular quadratic function, and this matrix A transpose A is always positive semi-definite. Why is that the case? Because A transpose A, X transpose X for any X can be rewritten, as A of X norm square. So Euclidean norm is always larger than 0. Therefore, this matrix is always positive semi-definite by checking this condition here. All right. So so that brings us to norms. So norms are always convex. And so for those who are familiar with this LP norm, so it is defined as follows. So you take piece power, and sum everything up, and then take piece root. Okay, so that gives you a norm, and for any p that are greater or equal to 1, then this this function is a convex function. You can check this easily by definition and by the triangular inequality of the definition of norms. In fact, any norms are convex functions. Specific cases that we're interested in are one norm, which is the sum of absolute value of the vector, and the infinity norm, which is defined as the maximum of the absolute value. Euclidean norm when p is equal to 2, that measures the Euclidean distance between this point and 0. For matrices, we can similarly define the something that's very similar to p norm on the spectrum of this matrix. So by spectrum, I'm referring to the singular values of a matrix. So for those who are don't know what I'm talking about when I talk about singular values, yeah, please go over the review slides on linear algebra and numerical linear algebra to see that you can always decompose any matrix using singular value decomposition, and the diagonal matrix in the middle collects the so-called singular values. In particular, the operator norms or spectral norm is defined by the largest singular value. So you can think about this as L infinity norm on the spectrum. Moreover, the trace norm or nuclear norm, so these norms will come back in the remainder part of the lecture and later for this course, is a sum of the singular values. So these are essentially the same as the one norm on the spectrum. So one particular thing that I like to talk about is that what happens when P is smaller than 1. Okay, so what happens is that when P is smaller than 1, then you no longer get something that's convex, right? So in particular, when P goes to 0, takes a limit at P goes to 0, so X L0 norm becomes the sum of indicator. So this indicator is a 0 and 1 indicator. When the condition is true, it returns 1, otherwise it returns 0. So sum over all coordinates of this X, and if xi is not 0, then you add everything up. So this essentially measures the number of non-zero coordinates. Clearly, this is not a convex function, because if you take the convex combination of two points that have only one non-zero coordinates, if these two coordinates are not the same coordinates, then taking the convex combination, it will give you something that have two coordinates being non-zero, right? So this is a violation of the definition of convexity. Therefore, this is not a convex function. Okay. So interestingly, sometimes for these kind of problems that deals with L0 norm or the rank of the matrix measured by the number of non-zero singular values can be solved by convex optimization problems by an interesting reformulation. Okay, so there's a question that I've seen P norm defined for matrices. Are those also convex? The question is yes, any norm, if you can say that anything is norm, so L0 norm is not a norm, so we call it a pseudo norm because it doesn't satisfy the triangular inequality. For any norm that satisfies the axioms of norms, then they are also convex functions in its argument. In this case, the argument is a matrix, right? So there are like different types of P norms that are defined by matrices. So the norms that I'm defining here are not the same as the typical P norm definition in matrices. So those are like Shetton P norm. So you'll see that on in later part of the lecture and also on Wikipedia. Okay, so more examples of convex functions. So indicator functions is an interesting special case of convex functions. So in particular, so indicator functions with this capital I. So previously that indicator function I used are with this 1. So it talks about when the condition is true, then it gives you 1. Otherwise, it gives you 0. It's like a Boolean function. This indicator function is different. So this indicator function outputs either 0 or positive infinity. So in particular, in this indicator function is given by a set C. So when C is convex, then its corresponding indicator function defining as follows is a convex function, right? To see this, just enumerate all the possibilities of X and Y, say in R, R to the N, right? So let's say that there's a convex set that's a subset of R to the N. So there are basically only a few cases that we can discuss. If both X and Y are inside C, then clearly the IC of Tx plus 1 minus Ty is equal to 0 and equal to IC of X T plus 1 minus T IC of Y, right? So why is it that this one is 0? And that's by definition of the function and by the definition of convexity, convex set, right? So what if one of these points or both of these points are not inside the convex set, right? So if x is not in the convex set, then well, we know that the right hand side of this equation is positive infinity. It's positive infinity. So anything is smaller than positive infinity, therefore it checks the condition of a convex function, which proves that this function is convex. Okay, so support function, so as we will see later in the class, is the so-called conjugate of the indicator function. So the support function is also a convex function. Like in fact, it is a convex function for any set, regardless of whether the set is convex or not convex. So this is a little bit hard to visualize geometrically, but support functions, you can think about it as the like the signed distance to signed distance of point x to the I guess a supporting hyperplane that passes through the origin of the space. So consider this is a convex set, right? This is convex set, and this is the origin, and this is your vector x. So the support, I guess the support function finds all the like supporting hyperplanes of this set from the origin that covers origin. Also, like it is tangent of this convex set right here, and then like you basically enumerate all the possible all the possible direction here. And then you find one that maximizes, I guess it maximizes you enumerate all of them. It maximizes the inner product of this x with this this function. So in this case, you will end up finding somewhere where x happens to be related to the normal of this indicator. So basically, if you take inner product of this with some point with this y here, then you end up getting the distance that's coming out of this inner product, right? So of course, so support function is closely related to the supporting hyperplane, and you need to work out the math algebraically to actually see the connection. And in addition, the max function that takes vector x and output the maximum coordinate is a convex function. So this is also like easiest to check by first principle. So some key properties of convex functions. Again, there are some equivalent definitions of a function being convex. So a function is convex if and only if its restriction to any line is convex. So this is saying that for multivariate functions with a surface that's multidimensional, you can restrict it to any direction, and then that carves out a particular univariate graph, right? So if a function is convex, if towards any direction and the restriction to any line, and that this, like in some sense in the subspace, and this function becomes remains convex, then this is a characterization of a multivariate function being convex. We can also characterize this in a slightly different way using definition of convex set. So we can say that a function is convex if and only if its epigraph is convex. So what is an epigraph? So let me visualize it with just a quick example. Okay, so let's consider this function, right? So is this function convex? Okay, so it's not convex. What is an epigraph? So epigraph, by the definition, say is epigraph is given by a particular parameter t, right? So the area under the curve, but above this function, is the epigraph. So in this case, we can see that this epigraph is clearly not a convex set. Therefore, this function is not convex. So this is one way to see this. On the other hand, if we draw a convex function instead, like that, so what this is saying is that this function is convex if all the epigraph, all t, are actually a convex a convex function, right? So there's another thing called the sub-level sets, right? So sub-level sets is closely related to epigraph. But the only difference is that now this is only a set on x, not a set on extended coordinate x comma t, right? So in these two examples, the corresponding epigraph is just a subset of the real line, right? So the epigraph here, the epigraph at this t definition is this. So it is a set that are, I guess, discontinuous. Therefore, it is certainly not this sublevel set is not a convex set. On the other hand, for this one, then there's a theorem that says if f is convex, then any of its sublevel set at any t happens to be a convex set. This is saying that this line segment is convex, right? So notice that the converse of a sublevel set theorem is not actually true. Can anyone come up with an example? Okay, so I see nothing in the chat box. So think about this function. I guess fx is equal to square root of x absolute value. So what does this function look like? Right. So it has square root on the left hand side. It has minus square root of minus x on the right hand side. So notice that this function have all its sublevel sets being convex, right? Contiguous and convex. But this function is clearly not a convex function because if you take these 2 points and linear interpolation is under this function. All right, so although this function is not convex, it satisfies some interesting properties in that it only have like one global optimal solution. So for those functions that satisfy that all their sublevel sets are convex, so we call them quasi-convex functions, and quasi-convex functions are as easily solvable as convex functions. So we'll get to maybe quasi-convex functions towards the end of the class. Okay, so there's a question asked about elaborate restriction to a line. So let me do that quickly. Okay, well, yeah, I think whenever I switch back and forth between two things, so there are some unstable connections in the voiceover. So I'll try to just wait for 2-3 seconds before I start talking again. So think about the two-dimensional function, right? So think about the two-dimensional function, say a quadratic function that looks like this, where this is its minimum. I'm drawing the contours. Okay, so by a restriction to a particular line, so this is x1, this is x2. Okay, so it's two-dimensional. By restricting to a particular line, this means that we are taking I guess, a snapshot of this function on, say, this plane. And this plane is x2 equals to x1, right? So this is a one-dimensional line. And what this line is doing is that it cuts through a particular graph. Let me use a different color. So it cuts through a particular graph inside this line. So this is a restriction to a line. And this line happens to be, I guess, x2 equals to x1. Okay, so I hope that clarifies the all right, so let's move further. There are other, like, arguably more useful ways of talking about convex functions and proving convex functions, especially when the function itself is differentiable. So we can actually use calculus to show that whether a function is convex. So how we're going to do that are there first order characterization of a convex function. So if a convex function, if a function f is convex and differentiable, then this is an equivalent definition for any pair of x and y, then it satisfies this first order optimality condition. So let me illustrate that a little bit. So think about this as a Taylor expansion of this function f of y at location x. So you take the Taylor expansion of f of x, you take the first term that is a linear approximation of f at location x. So visually this like this is a function f. So at this location, I'm now drawing like a linear line. So the direction of this is it's a gradient of f of x, right? So along this gradient direction, so I'm finding for any point y. So what the definition is saying is that if you draw a linear approximation of f at any location, then that serves as a valid lower bound. So this is f of y. F of y is smaller than the x plus this linear term, which evaluates at this point. All right, so the second order definition of convexity applies whenever f is twice differentiable, right? So if you take the first derivative, you get a gradient. If you take the second derivative, you get a Hessian. So anyone can tell me the definition of Hessian and what's the dimensionality of Hessian? Like suppose f is a mapping from R to the N to R. So what's a definition? What's a dimension of the second derivative? Just type it quickly in the chat box. Yeah, excellent. So this the dimensionality is n squared, so it's actually a matrix of n by n, right? In particular, there's a characterization says that if f is twice differentiable, the Hessian exists. Then f is convex if and only if the Hessian is positive semi-definite. Okay. A closely related concept that people might be familiar with from statistics and mathematics is Jensen's inequality, right? So if f is convex, then any random variables that you can define on the domain of x satisfy that f of x, if you put the expectation inside, is smaller than expectation of f of x itself. So like for me, I can never really remember the direction of Jensen's inequality until I learn a convex analysis and convex functions. Now it becomes extremely easy to remember Jensen's inequality. So I basically draw a convex function and then takes a linear interpolation of that. And the top line is expectation of f of x, and the bottom here, this location is expectation of x. So the bottom is f of expectation of x. So by doing this, I can always remember the direction of the Jensen's inequality, so you don't make mistakes at all, right? So I guess this directly follows from the axioms of a probability that the coefficients of these linear combinations are always inside this expectation is always non-negative, and then also they sum to 1, so it remains a convex combination. Okay, next slide. In particular, so if There are composition rules for convex functions. So if we are given a bunch of convex functions, we can use the following rules to construct new convex functions. So these will come handy from time to time. In particular, say you have f1 to fm that we know that they are convex. So if you take any non-negative linear combination of these functions, then that remains convex. Point-wise maximization, if each individual function f of s x is convex, then the point-wise maximization remains convex. That's defined by this. So let me give an illustration of this with just two functions. Suppose we have function f1 that's convex. We have function f2 that's convex. What is the point-wise maximization? So the max of f1 and f2 is this line, right? It's this part of the function. So you can clearly see from this example that point-wise maximization remains convex. Partial minimization is yet another thing that preserves convexity. So consider a bivariate function that's given by two variables x and y. So g of xy is jointly convex in x and y, and if the domain of this function is convex, then we can show that if we minimize over any convex set by eliminate one of these variables, then the function, the reduced function that contains only one variable is convex, right? So you can see this from the previous example of restriction to a line, right? So if you restricted that line to just the standard coordinate direction, then that's essentially the same as doing that's essentially the same as restricting it to one particular direction. And what this is saying is that you can further minimize it towards that direction and eliminate it instead of by restriction, you eliminate by finding the minimum. And the trajectory of the minimum in the other direction remains a convex function. So some examples of the previous two statements. Distance to a set. So it turns out that we can take either the maximum distance to a set or in some sense the minimum distance to a set, and then the function with both max and min are actually convex functions. So how do we see this? So in the first in the first example, so notice that we have already seen that the arbitrary norm from the axioms of norms is a convex function. Therefore, if we take the maximum of all the convex functions indexed by y, and that remains a convex function of x, right? So for each fixed y, so this is a convex function on its own right. So this is a point-wise maximum of this norm function. Okay, so there's a comment saying that the audio cut out from the beginning of the slide for me. So is that a general statement? Is that true for every slide? Okay, so I think what happens is that sometimes, like when the connection is not stable, it is showing on my screen that it says unstable connection. So when that happens, I'll just stop for a little bit until it goes away before talking. All right. Yeah. So if connectivity is an issue, I'll make sure that I talk to Comcast and talk to the part of the university that's dealing with this to ensure in future lectures it's better. All right. So let's go back to the slides. So think about this. So we've already proven using the pointwise maximum rule that this maximum distance for the maximum distance in a convex set from any point x is a convex function, right? So now let's work with the minimum. So notice that so the norm function with both x and y parameterized is jointly convex in both x and y. So this is a bivariate function. Then eliminating one of the variables y by taking the minimum gives us a convex function in x, right? So this is direct application of the previous rule. So this is also like the projection problem. So we wanted to find the point that minimizes Euclidean distance between between this set and this given point x, right? So we want to project x to convex set C. So there are more operations that preserve convexity, specifically like affine composition of affine composition preserve convexity. So this is very useful. So the previous one is an example where f is just a norm, and inside the norm you have two variables as the affine transformation of the vector x xy, right? So x minus y is the affine transform of the vector xy. So in this case, this is just a more general statement saying that if a function f is convex, then g of x, when the argument of x is the affine function of x, then g of x remains convex. More generally, we can use calculus to come up with a set of sufficient conditions that retain convexity when we compose functions. Okay, so first of all, people may not be familiar with this notation. So this notation h of g. So basically, this notation means that I'm passing the output of function g to h g of x is equal to h of g of x, right? So there the general rules that are dealing with these compositions involves checking the convexity and monotonicities of h and the convexity of g in order to tell whether this function composed function f is convex or concave, right? So it is a little bit difficult to remember. So I keep coming back to these slides whenever I need to apply these rules. But one potential way that you can remember this is through the chain rule in calculus. So let's try to work it out so that we remember how to do this. So let's add a page. So consider a function. Well, let me h. Yeah. So yeah, let it be. Okay, so let's maybe consider the two cases, the cases when h and g are both differentiable, right? Second or twice differentiable, so that we can apply the second order condition. So if h compose g, second derivative is larger than 0, then hg is convex. Okay, so let's try to apply this rule by working out the second derivative. So let's first take the first derivative. The first derivative by the chain rule is, I guess, h prime and g, okay, and then plus h g prime, right? So now let's take yeah, sorry, I messed it up. So h g of x multiply with g x, right? So now let's take the second derivative. So when taking the second derivative, this is a product of two functions. We need to first take it for the first function, multiply with the second, and take the keeps the first and takes the derivatives of the second, right? So this gives us h twice derivative at g of x. But then by the chain rule, we need this g prime of x multiplied with another g prime of x plus I guess h prime g of x G double prime, right? So if we combine these two, we get the square of this. Okay, so then checking convexity reduces to checking when this condition is actually non-negative. Okay, so let's try to maybe reproduce some of the conditions from the slides. So H convex. So this is saying that this is always non-negative, and since this is square, this is also always non-negative, and H non-decreasing. This says that this term is always non-negative. Now, if G is convex, then by the second order condition, the second derivative G is always non-negative. So we have two terms that are both non-negative, which implies that it is non-negative, which says that HG is convex. Right, so this is really the way to remember it. So you can come up with other rules. So H is concave and non-increasing. Right, right. Sorry, H cannot be concave. Otherwise, you don't get H is convex, not H non-increasing, and G is concave. Then in this case, you have greater than 0, smaller than 0 because it is non-increasing. But since G is concave, you have smaller than 0. Then these two multiply together is greater than 0. Then H and G is convex, right? So this is the right way of remembering the rule. So don't just remember the rule, remember the chain rule from calculus. So with that, you are able to reproduce everything. Okay, so there's a generalization of this into the multivariate function that's slightly more complicated, so I won't go over it, but this is essentially the same rules that you can apply, but now that the non-increasing and non-decreasing quantities are specific to every coordinate. So you need those to hold for every argument separately. Because in this case, the G is a vector function. All right, so you are encouraged to check that these are true by the chain rule from calculus directly yourself. So notice that the previous rule of composing different functions are sufficient conditions. It is not always the case that you are able to apply them to deduce whether the composed functions are actually convex. Right? So one such example is a log sum exponential. So you cannot actually directly apply the previous condition to show that this function is a convex function. So this is a somewhat like one of the most interesting convex functions that people can will come up with. So it is defined as follows. You have a log of sum of exponential function of fn functions. Right, so first of all, it suffices to consider replacing these fn functions. It suffices to replace these fn functions with just say a change of variable ui, and then talk about the log sum of exponential function with respect to vector u. Right? Why is that? Like we're basically applying the previous condition of if this function g is a convex function, then substitute u with any affine transformation, then it remains convex, right? So so we can basically do that. So now, so how do we show that log sum exponential function is convex? So in fact, you can prove this by by checking the Hessian and showing that this Hessian is non-negative. So I won't go into the details, but these are the calculations. If you can show the Hessian is positive semi-definite, then you can show this log sum exponential functions is convex. So I wanted to like spend a little bit of time to talk about this log sum exponential function further, because we will encounter this in future lectures, and this is like in fact a very interesting function. So let's go to the board again. All right. So again, we're dealing with functions of the form log sum exponential of any input x xi. All right. So so this is a function of, say, f of vector x. This is how it is defined. This function is also often called softmax. So I'm going to show you why it is called softmax. So notice that this softmax is not the same if you're familiar with the softmax transform in machine learning. So this is not the same as a softmax transform, but I'll talk about softmax transform in a little bit. Okay, so this is closely related to the maximum of xi, right? So I argue that this is an approximation of max of xi. On the other hand, the max is not differentiable, but this one is. It is a composition of elementary functions, and everything is differentiable everywhere. So that's a good property. We can somehow approximate the max function using something that's differentiable. But why is it an approximation? So first of all, log sum exponential is, well, log is a monotonic function, so I can clearly see that this is smaller than log of the basically exp of x with its index replaced with argmax of xi, right? And that gives me max of xi. Similarly, I can upper bound this with something related to max of xi as well, because I can, I guess, upper bound it with log of I guess n multiply with max xp xi. What does that give me? It gives me log of n plus max I xi. Right, so even though we cannot like differentiate with respect to max I, we have something that's pretty good. So so it differs from max I only by a logarithmic factor. Now, soft argmax. Okay, so soft argmax function is a transformation of Rn to Rn, where Rn is a probability. So it's actually transformed to a subset of Rn that's always a probability. So how is soft argmax defined? So it is defined by e to the xi given sum of e of xi. So notice that this always gives you a probability no matter what x is. Okay, so let's now compare this to the argmax function. Again, argmax functions gives you the coordinates that that maximizes this objective function. So we can do the one hot representation of this coordinate using say take an example, x equal to 1, 3, 2. So this is a vector 1, 3, 2. The argmax functions taking x outputs 0, 1, 0. I mean, the location of this 1 indicates which coordinate is it, right? So this is argmax. Correspondingly, this soft argmax would give us e to the 1, e to the 1 plus e to the 3 plus e to the 2, and e to the 3, e to the 1 plus e to the 3 plus e to the 2, and e to the 2, e plus 1, e to the 3 plus e to the 2. So that gives us different probabilities that are pretty similar to 0, 1, 0. When x, when the dominant x is significantly larger than all the others, then this prefers this exponentially. So arguably this is a very good approximation, exponentially good approximation of this argmax function. On the other hand, this soft argmax is differentiable. So it is this soft argmax function that is what people call the soft max transform in machine learning. Okay, so that concludes the part of the lecture on convex functions. I hope these illustrations and these proofs help you to appreciate and understand what convex functions are, and how do you construct convex function, how do you tell whether a function is convex or not from the composition rules and from the first principle of definition, and also by using things like first order condition and second order conditions of convex functions when things are differentiable or twice differentiable. Okay. So if you have any, I'm gonna move forward because we have a lot of grounds to cover today. But if you have like questions, yeah, please write it in the Zoom group chat. Okay. So in the remainder of the lectures, I'm gonna be talking about convex optimization. I'm gonna go over the basics notation of convex optimization problems and how do we tell whether an optimization problem is convex, and how do we convert non-convex functions in non-convex optimization problems into convex optimization problems. And again, we'll be talking about things like operations that will preserve convex the convexity in terms of the optimization formulation. So we'll be having a lot of fun with the examples of convex optimization problems and what are the operations that we can use to reformulate it so that it remains convex. Okay, so I'm gonna skip this review slides because we just talked about it. So we talk about convex set and convex functions. So with a composition rule, you should be able to tell like whether these two functions are convex, right? So this is a complicated shaped function, but if you apply the rules that we've learned before, then you should be able to argue that whether this is a convex function or not a convex function. Okay, so I'll leave it as a quiz, and please, if you have a conclusion, just post that on Piazza so other people can get the benefit of it. Okay, so I'm going to be talking about terminology and talk about the first order optimality condition and talk about transformations, and also I'm going to give a lot of examples. Okay, so this is something that we looked at before, right? So we talk about the general form of a convex optimization problem. It starts with an objective function to minimize, so which we call f. So we are minimizing this objective function subject to a set of constraints. And this set of constraints can be broken down into two pieces: the inequality constraints and equality constraints. And so any convex optimization problem can be rewritten in this form. Well, in particular, this GI are if f and GI are both convex functions, then this also certifies that this optimization problem is a convex optimization problem. So we're using the term optimization problem, but in the like operations research literature and in the core optimization community, so they often call these programs, right? So linear programs, quadratic programs, semi-definite programs, SOCP, the second order clone programs, and things like that. So these programs are not computer programs, but rather it uses the notion of program from planning and problem solving. So if you can program something, it's like you are able to write down what is it that you're optimizing subject to what constraints. So we'll be using optimization problem and optimization program interchangeably in this course. And whenever we refer to computer programs as a piece of code, we will be using algorithms or code rather than programs. Okay, so f is called objective function or criteria. The evaluation of f is called the criteria value. And GI are called constraints, inequality constraint functions. Notice that GI is always smaller than 0, so we can get away with converting any other form that is non-zero on the right-hand side into this thing called into the same form. And D is the domain of how these functions are defined. So for the interest of this class, we'll be just calling the r to the n, right? But this is abstract, but we wanted to base our thoughts and intuition on the particular vector space, the Euclidean space r to the n. So for now, let's just call this the r to the n. For different x, we can find whether x is feasible or not feasible. So a feasible solution to this optimization problem is one that is within the constraint set, that one that satisfies the conditions given by GIs and given by the linear constraints ax equal to b. Moreover, we use the notation of f star to denote the optimal objective function value. Okay, so whenever there's a star, it means something that's optimal, and whenever we have x star, so that means that we are writing down one particular solution that achieves that optimal value, right? So implicitly, that also says that this x is a feasible point. Okay, so we call x or x star optimal or a solution or a minimizer to this convex optimization problem, or to this optimization problem without worrying about whether it is convex. So implicitly it is feasible, and sometimes maybe finding a solution that is optimal is difficult. Then we want to characterize for each solution how optimal is it. So we use this condition called epsilon suboptimal solution by saying that this x is feasible, and at the same time this f is at most epsilon away from being optimal, measured in terms of the objective functions that we're minimizing. Okay, so if x is feasible and gi x is equal to 0, then we say that this inequality constraint gi is active. This is a term that's inherently formed from linear programs when these gi's are all like affine functions. So in this case, this says that this particular solution is on one of the facets that's carved out by the constraint set. So it's on one of the faces of the polytope that denotes the feasible region of the linear programs. Okay, so any convex optimization problem can be reposed as a concave maximization problem. This uses the fact that minus f is actually concave. So we can talk about minimizing costs or maximizing revenue, right? Subject to our operational constraints. And no matter whether we are maximizing a concave function or minimizing a convex function, we all call these problems convex optimization problems. Okay. So it should be greater. So there's a question from Edwin saying that it should be greater than equal. What do you mean? So can you elaborate a little bit? Are you talking about ILP, or are you talking about? It's not like a greater than equal. So think about why this is the case, right? So we wanted we want this epsilon suboptimality condition to be some kind of guarantee of how good this solution X is, right? So it needs to be, since we're minimizing f, we need to minimize it to some extent. So having an upper bound of the solution value at X bounded by the optimal objective function value plus epsilon is saying that this X is guaranteed to be at least this good, right? So does that make sense to you? Okay, let's move on. So the solutions of a convex optimization problem may or may not be unique, right? So we use this argmin function to denote the set of all solutions of convex optimization problem. So the output of argmin is a set, right? So we can talk about whether X is in the set or not in the set. So to see why the solution is not always unique, so you can think about, I guess I'll prove it visually. So think about you are minimizing a function that looks like this. right? So this is a convex optimization problem, unconstrained, and any point within this region, they are any point within this region, they are a valid, feasible, optimal solution to the minimization problem. Now, an interesting property of this set is that this set is always a convex set. So why is that the case, right? So you can actually prove this from the definition of convex set and from the definition of optimality, right? So take any 2 points, x and y, and say that x, y are both optimal. Then, well, any interpolation of x with t greater than 0 equal to 1. All right, so this is any convex combination of these 2 points needs to satisfy the condition that f of this is smaller than t of f of x plus 1 minus t of f of y. But notice that both x and y are optimal. So that is saying that this is smaller than t of f star plus 1 minus t of f star equal to f star. Well, if this point, clearly it is feasible because the feasible region is a convex optimization, is convex set. This point is clearly feasible. Now that this point is smaller or equal to f star. And since f star is optimal, then on the left-hand side, this must also be f star, right? So this shows that the interior of any solution set must be a solution on its own right. Therefore, but it checks the definition of a convex set, saying that the arc-mean set is always convex. Right? So notice that when f is strictly convex, then that implies the solution is unique, right? And it's very easy to see this because for any a pair of x, y, these inequalities needs to be strict. Therefore, there by contradiction, there couldn't be 2 points x and y that are both optimal. Okay, so example. So let's take the example of the original Lasso formulation. So notice that this is the constrained version of Lasso. Okay, from the original Rob Tibishirani's 1996 paper. So can anyone tell me whether this is a convex optimization problem and why? Yeah, if you want to answer, just unmute yourself. Or you can type in a no takers. Yeah, excellent. Yeah, thanks, Alex. So what Alex is saying that is a proof of the objective function value is convex. But how about the constraints? Why is the constraints convex? Can be converted to the standard form. All right. So notice that notice that this is not the standard form yet, but we can construct this g function such that the g of beta is equal to 1 norm minus s, right? So now this is a convex function because this is a constant, right? And this is convex. The sum of a constant function, constant with a convex function remains convex, right? So by doing this, we can rewrite this constraint into g of beta smaller than 0, right? And that gives us the standard form of a convex optimization problem. So so what is the so now I guess everybody know what the criteria function is, the inequality and equality constraints. So we don't have an equality constraint, but we have an inequality constraint. So so now the question is whether the solution is unique, right? Can anyone take these 2 questions? So first of all, let's make the assumption that we are in a situation where x, say n is larger than p, so x has full column rank. So then is this is this problem is the solution to this problem unique? Okay, so to see this, notice that this is a quadratic function, right? So you can from the previous calculation, we know that the leading term of this quadratic function looks like beta x transpose x beta. So first of all, we know x transpose x is always positive semi-definite by construction. But suppose n is larger or equal to p, and then full rank. That means that every coordinate of x is actually linearly independent, which says that this x transpose x p by p matrix actually satisfies that x transpose x is strictly positive definite. So yes, the answer to this is yes, it is unique. So what happens when we are in the high dimensional regime, when the number of variables are larger than the number of data points? So the answer is, well, not necessarily. So you cannot conclude that the solution is not unique, but you also do not, without knowing anything else, you also do not know whether it is unique. So we'll see more of this in one of the future lectures, where we can show that with probability 1 under any density that the solution to this is actually unique. If x is drawn from some arbitrary distribution that emits a density. But this is not directly seen from the formulation here, and it cannot be proven from strict convexity. What if we change the objective function into a Huber loss rather than square loss? What is a Huber loss? So I guess we have this is one norm. We have x squared, which looks like that. Huber loss is the interpolation between these two that says that near 0, you get a quadratic function, then it suddenly switches to the linear mode and shoot up. So this is a Huber function. So anyone can tell me whether the Huber function is strictly convex or not strictly convex? Why is that? Yeah, thanks. That's excellent. Yeah, so it's not strictly convex because there's this linear shoot up. So if you take the linear decomposition, if you take the linear interpolation here, then whatever in the middle do not actually have the inequality, strict inequality. Okay. So another example of convex optimization problem is the celebrated support vector machine that many of you might already be familiar with. So in particular, this is a constrained version of the support vector machine. Okay, so let's parse this optimization problem a little bit by looking at its objective function, its criterion value, and this set of constraints, and then we can figure out why is this a convex optimization problem. Okay, so to see this, first of all, we can tell that this is say a quadratic function, right? And it's also a norm. It's a squared norm. Therefore, there are multiple ways of seeing that this is strongly convex in beta. And this term is a linear term, right? So this is the same as a C vector 1. So this is a vector of all 1 with this Kasai vector, right? So well, Fn function is convex, and the sum of the two convex functions is convex. So now let's go to the constraints. So what do we have? We only have like inequality constraints here. So this is linear. This is affine. So this is also affine if you move this to the left-hand side. So everything remains a convex optimization problem. So this is how you check whether something is convex or not convex. So now the question becomes, is the solution unique? Right? So notice that we have 3 variables, and this part is a quadratic function, and this part is a linear function. Therefore, overall, so we can rewrite this as a quadratic function with a concatenation of beta 0, and cosine, right? But if we think about it, so even though for beta, the corresponding part of the quadratic function is like this identity matrix, so it's positive semi-definite, but we have really no control over how these other parts of the objective functions, whether they have any constraints. So this Q function actually looks like identity and 0, 0. Which means that we cannot actually argue that this is this is a strictly convex optimization problem. On the other hand, what we can tell is that the optimal solution, no matter what beta or cosize optimal solution are, the optimal beta, this coefficient vector, is actually unique due to this part. And suppose we change the objective criteria by adding beta 0 back with a beta 0 square, and adding something like that, right? Can someone answer whether this makes everything strictly convex? Okay, yeah, I guess it's not really a quadratic function, but then we can already add 1 here, right? For this beta 0, and then we can add we can if we evaluate the second derivative, we can tell that the second derivative of this is always non-negative. Therefore, you end up getting something that's strictly convex. Okay, so so we've talked about this in the previous lecture, and actually we came up with a first principle proof. So this is a key property of a convex optimization problem. I wanted to repeat it because this is really the main computational benefit. So any problem that you can formulate as a convex optimization problem, then we know that then we know that all local minima are actually global. Okay, so you can get away with local information such as gradients and the second derivative, and then certify the remarkable properties of global properties that overall, no matter where you are, like this local, this particular location that's locally optimal is always global, right? So you can again see this from the fact that the optimal solution set is always convex, and also see that from the interpolation point of view from the definition of convex function. So now let's talk about transformations of constraints such that we can rewrite things into different forms, and one of those forms might be more favorable, might be easier to solve than another. Okay, so take this generic form of convex optimization problem. You can always rewrite it by introducing like a convex set, right? So you can write it. You can refer to these constraint sets more implicitly with a set that's carved out by the intersection of the convex sets that are given to you by the set of n+1 constraints. Okay. So equivalently, we can make it a completely unconstrained objective function by using the indicator function. Okay, so recall that indicator function gives you positive infinity when x is not in the convex set C, and it gives you 0 when this is in the convex set C. So these two are just the more opaque but equivalent definition of generic form of a convex optimization problem. So now let's talk about optimality. So it turns out that for any convex optimization problem, so we've already said that this is just yet another generic for formulation. So for any convex optimization problem, we can get that the optimal solution X needs to satisfy this condition in a form of an inequality that holds for any y that's feasible. So this is what we call the first order condition for optimality. Okay, so let's maybe see that a little bit more clearly by proving that this is the case. Okay, let's work on first order. Okay, so so what it is saying is that for differentiable f, f is convex. Okay, then x inside arc mean of f if and only if it satisfies that the gradient of fx transpose y minus x is greater than 0, is non-negative for any y inside the convex set C. Okay, so how do we prove this? So first of all, let's use the first order condition of a convex function, right? So f convex by first order optimality by the first order criteria of the convex function that we can write f of y is larger than f of x plus gradient. So again, this is simply doing Taylor series of expansion. Okay, so this is always the case. Now let's apply let's apply this condition here, which allows us to say that this is always larger than y, and since this is true for any y, thus x is optimal. Okay, so I've proven the right hand side to the left hand side, and I'll leave the left hand side to the right hand side as an exercise. All right, so a particular special case of interest is when the problem is unconstrained. So it's when n is c is r to the n. So how do we see this? So okay, so this is well equivalent to that for any a, right? Since x is fixed and the constraint is r of n, we can use y like for any such a, we can construct a particular y such that y minus x is equal to a, and the set of all these is r to the n. It's r to the n, right? So we can write this, but this is also equivalent to is equal to 0. Why is that the case? Because we need both a and minus a to satisfy this condition, right? So but since this is true for all a in R of n, then that is equivalent to say the gradient of fx is equal to 0, right? End of proof. Right, so that gives us the optimality, first order optimality condition for the case when f is differentiable and unconstrained, right? And that should be familiar to you from high school, that if you want to solve an optimization problem, takes the gradient to be 0 and assign it to takes the gradient and assign it to 0, and solve this equation, nonlinear equation. Yeah, for quadratic functions, we can calculate the gradient, and when Q is positive definite, then we know that the solution is unique, and we can write out the solution by solving a linear system of equation. When Q is not positive definite, but rather maybe positive semi-definite, meaning that some of the eigenvalues of Q is 0 or are 0, then we know that if B is not really in the column space of Q, then there's no solution at all. So how do we see that? So there could be some X that's in the null space of Q, such that you can make it arbitrarily large, right? And when you make that arbitrarily large, this particular linear term will end up shrinking to minus infinity. That's why there's no solution. What if Q is singular, but B happens to be inside the column space of Q? So in that case, there are infinite many solutions that forms a particular subspace, like affine subspace. Okay, so this is the description of all the set of all solutions that minimizes this quadratic function. Okay, so it's a good example to see. And the Q star is like Q plus is what we call the pseudo inverse of Q, which project B to the which first project B to the column space and of Q, and now it becomes invertible, and then you invert it in the basis that defines a column space. So now if we move to the general equality constraint minimization, so many of you might have seen the principle of Lagrange multipliers and method of Lagrange multipliers to deal with constraint optimization with the equality constraints. So what you might have seen from there is that the optimal solution is characterized by this equation, right? So there exists some U such that the gradient, if you plus A transpose U, is equal to 0. If you can construct such as U for a particular X, then that certifies that X is optimal. And if you can solve this equation jointly with unknown variable X and U, then you can identify the optimal solution. So let's apply the first order optimality condition here, and then see that this is actually and see that this is actually the case. Okay, so all right, so first of all, by wait. Okay, this is good. By first order optimality condition, we know that the optimal solution X satisfy any Y such that AY is equal to B. Okay, so I claim that this condition is equivalent to say that the gradient of f of x transpose v is equal to 0 for any v inside the null space of A. So what is the definition of null space, right? So if v is in the null space of A, then A right multiply this v is always 0. Right, so this is a definition of the null space. And why is this equivalence? Okay, like we said previously, so if this problem is feasible, then this AY equals to B, the solution of the feasible solution can be characterized by all the solutions will satisfy say X equal to A pseudo inverse B plus some V, where V is in the null space of A. Right, so this is a set of all solutions, and both X and Y needs to satisfy this, which means that Y minus X is equal to A this V plus this V correspond to Y minus A pseudo inverse B plus this V correspond to X, right? Which these two terms got canceled out, you get Vy minus Vx. Yeah, but both these two are in a null space, and null space is a subspace. Therefore, this is also something in a null space, and you can use the difference of this to construct any point in this null space, which gives us this equivalence. Okay, so now that we have this equivalence, what this is saying is that this vector gradient of f at x is actually perpendicular to every single point in this null space, which is saying that this is perpendicular to the entire subspace. Okay, so if that is the case, that this also says that this gradient of fx is inside the orthogonal complement of this null space, which happens to be the row space of matrix A, right? And the row space of matrix A is a column space of matrix A transpose. And what this implies is that there exists some coefficient U such that for any for a particular basis function that spans the column space of A transpose, so one particular basis is just A transpose, such that f of x is equal to A transpose U. So this is taking the linear combination of the basis functions, and that gives us construct this gradient of f of x. And what is this U? Okay, maybe let's call this U tilde. Then we have constructed in the U to be minus U tilde by substituting this, and we get f of x plus A transpose U is equal to 0. And this is the method of Lagrange multiplier. Yeah, I hope this is clear to everyone. All right, so let's move on. Projection into a convex set is a convex optimization problem, right? So clearly you have a quadratic function to minimize subject to a convex set. So I'm gonna skip the details, but you can try applying the first order optimality condition here, which would give you a condition that looks like this equation here, right? So remember that we talked about a particular convex set of interest called the normal cone. So the first order optimality condition is equivalent to say that the difference between this input A and the optimal solution X is always inside the normal cone. So I'm gonna like maybe visually illustrate this. So suppose suppose this set is a convex set C, right? This is the A that you want to project to this convex set. So what happens is that you're gonna find the point that's inside this convex set is closest to A. So that would be this particular point, X star. Okay, and this is perpendicular, right? So what is a normal cone? So the normal cone at X star happens to be this cone, this ray, right? This is a cone or ray, right? And what it's saying is that A minus X is inside this convex set. What if A is right here? Okay, so the closest the closest point in this convex set from A is this particular point. All right, so if we connect these two, A minus X gives this direction. And what this is saying is that this vector is inside the normal cone that's given to you at when you NC of X. All right, so I hope geometrically at least this is clear, and this is providing interesting like geometric insight that we can connect the first order optimality condition to things that we've learned in the last lecture. So there are other operations that preserve the convexity and also preserve the convex optimization problem. So suppose we have optimization problem with two parameters, with two variables, x1 and x2. And if we can somehow if we can somehow analytically evaluate the optimal solution of x2 and substitute it as into the formula as a function of x1, then we can eliminate that that variable, right? So this follows directly from the principle of partial minimization in the rule of convex function composition, and that gives us another convex optimization problem with additional variables removed, right? So so let's give a particular example from the support vector machine, right? So on top we have the support vector machine that's written as exactly the same as the one that's in the previous slide about support vector machine. So suppose we can rewrite the constraints, right? We can rewrite the constraints as this, and then we can replace the slack variables in the objective functions with this function max of 0 and 1 minus this quantity. So if you have taken like a machine learning class, so you will know that this quantity is closely related to the margin of this particular point to a linear separator defined by beta. And this function is the rectified linear function, right? So this max of between 0 and 1, so it's a rectified linear. So so visually, so this function looks like it is 0 if this input is non-negative, and it linearly shoots up if this function is positive, right? So this looks like a door hinge, and that's why it is called a hinge function. Okay, so so now that it is clear that support vector machines is actually just yet another like surrogate loss minimization problem that minimizes the hinge loss rather than the logistic loss that's coming from the logistic regression, rather than the square loss that are coming from the linear regression. But by doing this, we essentially have eliminated this Kasai parameter, and that's precisely because we can plug in the optimal Kasai into the constraint, so that now support vector machine becomes an unconstrained optimization problem. Now another example. So sometimes like we have an optimization problem that of the following form: minimize of fx when f is not necessarily convex, right? So we can always transform an optimization problem into another, like without changing the optimal solution, if the transformation of the objective function is like a monotonically increasing function. Okay, so this is easy to see because by adding this h, then we are basically doing isomorphism of this function. So there's a one-to-one mapping, and everything the optimal solution that minimizes f of x is also the optimal solution that minimizes h of f of x. So one particular example that I can give is in the context of statistics is that often we want to maximize the likelihood as a function of like this is your observed data x1 to xn, and your model's parameter theta. You want to find the parameters that maximize the likelihood of observing this this realization of random variables. Okay, so the likelihood is often not a convex function, but what people do typically is to do a monotonic transformation by converting it to the maximization of a log likelihood as a function of theta. So suddenly the log of likelihood is a concave function. So you can maximize a concave function and use like any algorithm you like, and you end up getting the local minima, which in turn is a global minima. Okay, so Now, another example of such transformation being useful is to define a family of problem called the geometric programs. So geometric programs are not convex optimization problems, but we will see that they can be converted into convex optimization problems. So they are dealing with functions that are somewhat strange, called monomials and polynomials. So you should know what a monomial is. So it's a polynomial, it's a specific type of polynomials that only contains polynomial of variables, but no no other terms. So basically one of the polynomial basis, monomial basis is positive, and everything else are zero. Polynomials, on the other hand, are a family of polynomials where your coefficients of the monomial basis function are non-negative. So you get a sum of monomials, which called polynomials. So this is a positive coefficients, polynomials with positive coefficients. That's why it's like people created this word called polynomial. That sounds really weird. So a geometric program is of the following form, right? So you have an objective function fx to minimize, and you assume that this fx is a monomial. So notice that this can be arbitrarily non-convex. So it's really a really strange kind of optimization problem, and subject to constraints where gi's are polynomials and hi's are monomials. Right, so this is a family of programs called geometric programs. So how do we solve it using convex optimization problems? So notice that when fx looks like this, we can rewrite it by we can rewrite it by doing the change of variable by replacing x with e to the power of yi. So you can always do this because e is monotonic. Right? You can always convert x1 by making it y1 and e to the power of y1, and then we'll be solving an equivalent optimization problem. So with this transformation, then we can write every monomial as e to the power of some kind of a affine transform of y, right? And now let's, in addition, take the logarithmic transformation and apply this monotonicity conversion of the previous slide. Then we get a log sum exponential in the objective function. And we've seen that the log sum exponential is a special kind of a convex function. Therefore, like this is a convex objective. So how about the constraints? So by taking by taking the like log transformation, and also by taking adding the additional log in the outside, and using the fact that the right hand side is smaller than 1 and log of 1 is smaller than 0, then we essentially have converted the geometric programs into the standard form of convex optimization problem, right? So there are a lot of problems that you otherwise sort of not a convex optimization problem that can be converted in this case into a convex optimization problem. So the typical application of GP is to solve this, some kind of floor planning problem. You want to find the smallest space, rectangular space that's available to put in all your furniture so that you can minimize your rent. And some of the furniture needs to have size constraints, and you want your chair to be always in front of your desk, and you want your bed to be always next to the window, and so on and so forth. And so all these constraints can be encoded as a geometric program. And then once you convert it to a convex optimization program, you can solve it using convex optimization tools. Okay, so other transformations include, I guess, so I'm gonna like take at least 10 more minutes. So if you need to go, just go, and then there will be videos that are available. But I do need to cover some ground in order to make the right progress for the course. Okay, so we can eliminate the equality constraints by like using the I guess if it is feasible, then we've already seen that you can always represent it as a solution of this form multiply plus something that's in the like this is A pseudo inverse B, and this is a particular basis of the null space of A. Okay, so by doing this, we can always convert any feasible solution into something of this form, and then by replacing X with a different variable that's of a lower dimensional in a lower dimensional space, we can convert the previous problem into a convex optimization problem without the equality constraints. So you can always do this. The issue is that like this is fully general, but it's not always a good idea to do this because this additional transformation of M may make the problem a lot harder to solve. Okay, so also we can eliminate the inequality, the complicated inequality constraints by introducing slack variables, right? So instead of so support vector machine is one example of that. So you can introduce slack variables Si and then convert this Gi X into into a equality constraints. So notice that once we do this transformation, this is no longer a convex optimization problem in its standard form. And the reason is the following. So Gi is a convex function and Si is a linear function. So the sum of this is a convex functions. But remember, in the standard form of the convex optimization problem, this needs to be an inequality. So this needs to be an inequality. But now we have equality here. Therefore, it cannot possibly be a standard form of convex optimization problem. But this is equivalent, right? So you can always convert this into a convex optimization problem in its standard form. And this type of this type of transformations that eliminates inequality constraints is often it's often needed and are necessary in linear programs, and people think of these different type of transformations. So in those cases, this Gi are linear, so you are basically converting linear inequality constraints into linear equality constraints so that you can apply, say, the method of Lagrange multipliers or apply things like simplex method to solve this numerically. So we can also relax non-affine constraints into things that are affine. For instance, so sometimes we have so Hj of xi is equal to 0, and Hj is not an affine constraint. Often it is without loss of generality to actually replace this with an inequality constraint. So it becomes a convex optimization problem in its standard form. Okay, there are many cases you can do that, and the support vector machine example is just one of them. So another is the following maximum utility problem. So you can think about this problem as maximizing the utility function, where the objective function is the sum of different utilities, and x is your arguments on how much consumption that you want to use, and the constraints is subject to say f is like you need to invest the bt into the future so that you can get some benefit in the next iteration. And often this f is not a linear function, but f might as you increase bt, it may suffer some kind of a diminishing return, right? So when that happens, then f is a concave function, and minus f is a convex function. It always suffices to retain the problem to be exactly the same if we relax this constraint into t plus 1 is smaller or equal to the right hand side by simply replacing this equal with inequality. And that's not changing the problem at all. Okay, so there are other very interesting examples of how we can convert a non-convex optimization problem into a convex optimization problem. So I'll give like one such example, and then we'll call it a day. So this example is principal component analysis. So I assume that now that you are on the PhD level, you must have heard of the principal component analysis, like at least in one of the courses that you've taken before. All right, but you might not have seen the optimization formulation of the principal component analysis. Usually people taught principal component analysis algorithm to be, say, well, you apply the algorithm singular value decomposition or the eigenvalue decomposition, so then you can get the solution to the principal component analysis. It's like magic, right? But it turns out that singular value decomposition is actually solving an optimization problem called best rank K approximation. This is a highly non-trivial optimization and highly non-convex, because as we've seen, the rank function, just like a L0 norm function, is like the number of non-zero singular values. So it's extremely non-convex. And the F norm is what we call the Frobenius norm. You can think about this F norm by just vectorizing the matrix inside it, and then take the sum of the squares. So just vectorizing and then take the Euclidean L2 norm, right? So that's the easy way to see the Frobenius norm. So you wanted to find the best approximation R that's of rank K that approximate this given matrix X. So that's a problem of principal component analysis, right? So now that we've seen the non-convex optimization formulation of principal component analysis, can we actually like reformulate it as a convex optimization problem? This is not intuitive at all, right? It turns out that that you can, right? So first of all, you can rewrite the optimization problem by replacing this with some kind of projection matrix. So you instead of optimizing over R, you can optimize over the projection matrix, and this helps you to rewrite the exact objective function into the Frobenius norm of something else. On the other hand, like once you complete the squares and once you like decompose the square into the three terms, the only term that matters for the interest of optimization problem is the inner product of this S, which is the X transpose X. So that's an unnormalized covariance matrix. And the trace of SZ is the same as S and the inner product by taking the vectorized S transpose vectorized Z. Okay, so that's how you think about trace. So then you have a linear objective function. But now that the constraint set remains a non-convex set, because we want to find number of bound, the number of non-zero eigenvalue of this matrix to be to be K. But since Z is now a projection matrix, we know that its eigenvalues are either 0 or 1. So we can reduce it as a binary optimization problem, integer optimization problem. Okay, so it turns out that any such Z can be rewritten as VVK transpose, where VK gives the K columns of V. You can always do this. So we know that this Z is positive semi-definite. Okay, so with this observation, we can transform the problem by relaxing the constraint set into something of the convex Hall of this non-convex constraint set, and this relaxed convex set is what we call a fantope. Okay, so notice that instead of having this lambda to be either 0 or 1, so we are relaxing it into a continuous interval between 0 and 1. And by doing that, this suddenly becomes a convex set. And then this whole problem is relaxed into a convex optimization problem. You may ask, like, with this relaxation, are we losing anything? So remarkably, it can be shown that this the solution to this optimization problem is equivalent to the original non-convex PCA problem, as they have exactly the same solution. The proof of this involves, I guess, checking the first order optimality condition, and then certify that solution, proving that solution also solves the non-convex optimization problem. And this is coming from a result of key find about more than half a century ago. Okay, so a fun fact about this result and also about key find is that this guy, this mathematician, is actually a professor of mathematics in UCSB, like for 45 years, until he passed away in Santa Barbara. And the same guy is also famous for other of his mathematical contributions, including, I guess, his contribution to combinatorics and his generalization of the von Neumann's minimax theorem. Right, so this is very prolific mathematician of our own in UCSB. Okay, so I'm gonna so this is, I guess, the last slide I'm gonna talk about. So so having an optimization formulation of something that you otherwise consider only as algorithms has a following advantage, because now that you can make adjustment to that by adding things like regularization terms to introduce additional structure. So one particular thing that you can talk about is the so-called sparse PCA, where we want to prefer a small number of principal components that are sparse, and that allows you to work with high-dimensional data in ways that are more efficient, right? So this is a valid problem to solve. And sparse PCA, like the first optimal algorithm, the first algorithm that achieves the minimax rate for the problem of sparse PCA, like without going into detail what that problem is actually adapted from the convex optimization formulation of the of PCA itself. So by adding some kind of a L1 norm of this matrix Z, so we can end up solving the problem and with the same relaxation of these rank constraints. And that the argmax of this optimization formula happens to be the estimator that solves the sparse PCA problem in ways that minimizes the max error. Okay, so so that's the advantage of having an optimization formulation. And sometimes you can use convex optimization as convex relaxation to solve problems that are NP complete. So approximately, one typical example is max cut. So I'm gonna leave max cut to the next lecture. And well, that's it. So there are interesting reading materials that you should go over, but the slides definitely contain a lot of information that's enough for you to digest. So if you have done the reading and submitted the reading summaries, so I hope those reading summaries would help you to appreciate the lecture a lot more than you otherwise able to, right? And by the way, like this is the kind of lectures that we will be having, at least for the first half of the lecture. And if you have any comments, whether I'm going too quickly or I'm going too slowly, whether you want more proofs or less proof, whether some of the things that I'm doing is like too straightforward to you, just let me know, and I can adjust the pace of the lectures. All right, yeah, thank you very much. Yeah, there's a question about the video recording. So the video recording will be available later today. So as always, I'll be posted as an unlisted video on YouTube, so you guys have easy access, even if you're not on UCSB VPN. For reading summaries, like it's really not a lot of the evaluation. So you will get like 80% of what you would otherwise get supposed to submit on time. Right, for the homeworks, like our course policy is that you have like a total of, I think, 4 days of late days. You can allocate that at any of your homeworks. Yeah, check the syllabus for details. Yeah, for reading summaries, well, you get 80% if you submit late. Yeah, the point really is that for you to force you to read the reading materials before coming to the lecture, so that you understand it better and you get some more away from the lectures than you otherwise do. All right, thank you very much, and that's the end of today's lecture. Yeah, for those who have questions, feel free to post it in the chat or on Piazza. I'll gonna be responding to those questions asynchronously. All right, guys. Thanks a lot. I have another meeting coming up, so talk to you guys next Monday.